One of the larger, more complex subjects we're going to have to discuss is the oxygen sensor in the catalyst efficiency monitors. Now, the catalyst efficiency monitor and the oxygen sensor monitor are linked closer together. The catalyst efficiency can't really work without relying on the oxygen sensor up front to make it possible. So we can't really separate them. We're going to talk about them together. They're both oxygen sensors, and they respond to the same level of oxygen, even though they should have different levels of oxygen by their location. Let's go and see what we're talking about here. First of all, let's talk about what an oxygen sensor monitor is. It's a lot bigger monitor than most people realize. The first thing, we're going to be in the proper enabling conditions. Then we're going to look for stuck rich or stuck lean faults. This is a very simple. Oxygen sensor voltage too high, too low, doesn't move. Then we're going to have to measure the switch points. Where is this thing switching? And we're going to talk about and define exactly what a switch point is. We're going to look at rich to lean as well as lean to rich. Switch points, switch time. We're going to be measuring all that just like we're taking a lab scope. We're going to look at the big slope, which is an oxygen sensor test done by Chrysler, and the small slope, and the half cycle, and the full cycle, the rich amplitude, the lean amplitude, the time to activity to test the heater function itself, as well as heater current. All of that goes in to make up one monitor. Now, because the catalyst monitor is so dependent on normal oxygen sensor operation, let's discuss oxygen sensor monitors first. The PCM verifies the O2 operation prior to testing the catalyst monitor and prior to doing any testing. So even the PCM won't run a catalyst monitor without a good O2 sensor, and that's something you should be aware of. Sometimes we find oxygen sensor constant stored in mode 5, sometimes in mode 6. It's the option of the manufacturer. They can do it either way. What we're going to be looking for when we're looking at speed, heater operation. We're going to look at time, rich to lean switch times, half cycles in some manufacturers, lean to rich and big slope in some manufacturers, pre-cat heaters, pre-cat sensors and response time, after-cat sensors and response time, sensor stuck rich, time to activity, sensor stuck lean, heater operation, and the amplitudes. A ratio of allowed switching times is also used at times. All O2 sensor monitors test for the same thing, even though each manufacturer has their own way of doing it. So it's important to know what they're testing so we can duplicate their test. Our main function of the diagnostics behind mode 6 is to show you what you need to do to duplicate this testing. We'll look at the different definitions and then go over the diagnostics we can do to duplicate what they're doing. We're going to start off by looking at this chart. To understand everything mode 6 is telling us about the oxygen sensors, it's going to be necessary we go a little deeper into how oxygen sensors operate. We're going to start off by looking at this chart, which is graphing voltage on the right, 0 to 1 volt up the left side, to air-fuel ratio, 14.3 on the left, 15.1 on the right. And in the center is the stoichiometric point. At stoichiometric, about 0.45 volts, we have the ideal balance between air and fuel. This is for the narrowband oxygen sensor, also known as the NERT cell. Now, we have a minimum voltage level. When the mode 6 looks at this, the PCM is going to drive the mixture rich and look at the rich indication. It's going to take it out to about 14.4 to 1 air-fuel ratio. That's the max rich indication for these narrowband cells. What that means is if we go any richer, the line stays the same. So the voltage at this point is critical. It can be anywhere from 0.85 to 1.2 volts, but the minimum is 0.85. So when you see max rich, what the PCM has done is it had measured the voltage at this point to know where it is because it's a variable. And on the other side, this is also another point we got to remember. It cannot measure anything beyond 14.4. The reason we bring this to your attention is for wide open acceleration. Some people use this voltage to see if they're getting sufficient fuel flow. Well, the ideal or a good, reasonable number for wide open acceleration is 13.2 to 1 air-fuel ratio. There's no way for this to measure that level. So don't use this just for wide open throttle saying I got plenty of voltage if it gets to some number. Max lean is about 14.9, and the PCM is going to take the vehicle down and say, can it get to the maximum lean? The minimum level is 0.1 volt. If it doesn't get to 0.1 volt, it's not reading right. So we're going to be looking at voltages between 14.4 to 14.9. We bring this to your attention because we say, take it rich, take it lean. We're not talking what we used to call rich and lean, very low numbers, very high numbers. Now let's talk about what we're going to be seeing. Let's talk about the definitions that are going to be used by the various manufacturers. TID 6 at GM, for instance, with a number of SIDs, is time to activity. GM's method of evaluating the oxygen sensor is to look at the time to activity. So when you see time to activity as part of your definition, it's measuring the oxygen sensor heater activity. TID 82 is a ratio of measured and max allowed switching time, rich to lean. We're going to define that further, but we just looked at the chart. We've just defined max rich, we've just defined lean. Now it's going to measure the time between those two, and we're going to show you in a lab scope what that looks like. TID 5 is rich to lean threshold voltage, and we're going to explain that later on a pattern when we look at a DSO to show you how we measure that. The other under TID 5 is lean to rich threshold voltages. It's going both ways, rich to lean and lean to rich. TID 5 is also going to measure low voltage for switch time calculations and high voltage. We just said high voltage is about 14.4 to 1. Low voltage, all of those things we just looked at that chart. The next criteria is the time from rich to lean, or rich to lean switch time calculation, based on those low voltage, high voltage measurements we made. And again, all of this is taking place in that time frame of the air-fuel ratio of 14.4 to 14.9. Mode 5 is also going to lean to rich switch time. Is it going equally fast in both directions? Chrysler TID 11 is going to be used a half-cycle counter, and we're going to show you that on a DSO because it's easy to show you. It's very much like switching from rich to lean. The big slope, how fast is it moving between 2 points? As I was saying, big slope is the time between 2 points. The rich volts test, how high is rich? Just like we got through discussing with GM, it's going to see what the voltage is, full rich, and the voltage full lean. We need to know those in order to do the switch ratio of rich to lean and compare them between different sensors. We may be comparing front to rear sensors. There's a number of switch ratio tests we do. Ford's amplitude test is really a response time. We'll have to show you that on a lab scope because it's easier to see the pictorial. But it's going to measure the voltage amplitude in a timed switching test. And it's going to do it for both the left and the right bank. It's going to be doing switch points. And we're going to show you that on a digital storage oscilloscope because it's easier to see. We're going to have switch points for lean, switch points for rich. They're all going to test the operation and the speed between two defined points. They may have slightly different nomenclature of what they call the speed. Switch time, very simple. Big slope, half cycle, all of these are measuring the time between 2 points. Reaction time we will show you when we start turning from rich to lean. How long does it take to make the turn? What's the rich movement? What's the lean movement? What's the ratio between different sensors? And everybody evaluates heater operation. So our question is, what are you going to do to duplicate all of these tests? And what we're going to show you in the next section is how we're going to use a DSO to utilize this. We're going to take a DSO and we're going to go through all these different operations and explain them to you.